Hello, everyone. Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries and constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. Before we start, I want to mention that I was recently introduced to a company, Magic Mind, who sent me samples of their product that boosts energy and focus. The ingredients are all natural, including organic matcha green tea, lion's mane mushrooms, cordyceps, choline, ashwagandha, turmeric, and vitamin C and D. The product is well formulated and nicely packaged, a small bottle for a single dose that can be consumed in a few seconds. I found the product very useful to keep me focused, reduce stress, elevate mood, enhance cognition, and generally keep a healthy immune system. I found it particularly useful when I'm tired. There are no controlled clinical trials yet, but the company is working on it so that consumers can have excellent scientific data as well. I would recommend you try it and let the company know of your feedback. They love to hear from their customers. The product is called Magic Mind and is available in most online retail stores. You get 1 month for free when you're subscribing for 3 months at www.magicmind.com/Jan Scientific Sense. That is JAN Scientific Sense. And with the code EAPEN20, EAPEN 20. It's an extra 20% off, which gets you a total of 75% off. This only lasts until the end of January. So I would strongly recommend you try it. My guest today is Professor George Schatz, who is Professor of Chemistry and Chemical and Biological Engineering at Northwestern University. His research involves theory and computation as applies to problems in nanotechnology, properties of materials, macromolecular structures and dynamics, molecular self-assembly, optics, plasma science, materials physics, and biophysics. Welcome, George.
Hello, thank you.
Yeah, so you have done a lot in this area, from Caltech to MIT and now teaching at Northwestern for nearly 40 years almost.
Oh, even more. Like 48 years, yes.
And it's a complex subject. It's very technical. I was, as I mentioned, George, I was at Northwestern Graduate School Engineering briefly. Let me see, about 36 weeks at the tech building, on in a different area, obviously, and so most of my technical understanding has gone away. So I went into business and all that stuff. So I want to start with the paper that you sent me, and maybe that will set the context for our conversation. The optical properties of metal nanoparticles, the influence of size, shape, and dielectric environment. You say here the optical properties of metal nanoparticles have long been of interest in physical chemistry, starting with Faraday's investigations of colloidal gold in the middle 1800s. More recently, new lithographic techniques, as well as improvements to classical wet chemistry methods, have made it possible to synthesize noble metal nanoparticles with a wide range of sizes, shapes, and dielectric environments. So before we get the details of this, George, what exactly is a nanoparticle?
Oh, yes, very good question. Uh, well, okay, so nanoparticle means a particle that has nanometer dimensions, okay? Usually the nanoparticles that I have studied are in the range from 1 nanometer up to about 100 nanometers in size. So a nanometer is 1 billionth of a meter. Okay, so this is really small. Okay, it's much smaller than, say, the diameter of a human hair. Okay, it is small enough so that these particles would actually be invisible if you had them suspended in water, unless they have some sort of optical absorption of their own. Okay, so in other words, they don't scatter very well. There's an effect called the Tyndall effect that goes back to the 1800s that refers to suspensions of particles and they can scatter light. But the metal nanoparticles have especially strong optical properties because they can absorb the light. Okay, and so that's kind of something that is related to what you just talked about. It's actually a phenomena that people have been aware of since prehistoric times. Okay, the best examples of that are stained glass windows in cathedrals. If you see stained glass that is red, especially for the cathedrals in Europe and other places, then very likely what that refers to is glass that has nanoparticles of gold that are suspended in the glass. Okay, and if the color is yellow, then very likely that refers to nanoparticles of silver that are suspended in glass. And the other colors are other metals, but those are the two metals. Uh, Okay, plasmon is a term that just refers to the type of excitation of the electrons in the metal. So you've got, silver and gold, they have electrons, and it turns out you can excite the electrons. And it's a term that was invented in the 1950s, actually, to refer to the red color of colloidal gold and the yellow color of colloidal silver. It's funny it didn't get somehow a name before that, but in any event, that's the term that was invented to describe these optical excitations. And the reason that that term was used is because the electrons in gold and silver and other metals are a little bit like what you find in plasmas. So plasmas are lightning bolts or spark plug, uh, you know, uh, when you spark something, you see a little flash of light, and what that refers to is, in the case of gaseous plasmas, to the sudden production of a bunch of electrons that are in the air. And it turns out that those have optical properties. Usually, for the case of lightning bolts, it's just sort of a whitish color. But in the case
Yes.
of metals, it turns out, gold has this characteristic red color, and silver has a characteristic yellow color. Okay,
So George, so let me try to understand this a little bit. So how are the nanoparticles created? So you know,
uh,
I think we mine for gold and we mine for silver.
yes,
Um,
yes,
and I have seen bars of gold and bars of silver.
right.
Where do the nanoparticles come from?
Yeah. So what happens is that if you take the bars of gold or bars of silver, you can dissolve them in very strong acids. Okay. And when you do that, you end up producing silver ions and gold ions that are in water. Okay. And when you do that, actually you though they're not very interesting solutions. They look a little yellowish. It's not terribly exciting to look at that. All right, and that's because it's ions, individual atoms of gold that lost an electron, they become ions, and those are floating in solution. But then what you do is you add something we call a reducing agent. So this is some molecules, usually they're just simple organic molecules like citric acid, okay, that you can add to the solution. And it turns out that if you heat that solution up with the citric acid, then the organic molecules will donate electrons to the silver ions or gold ions and turn them into silver atoms and gold atoms. And then what happens is that these atoms don't just stay as individual atoms in water, but instead they start aggregating. And they will make then, after you aggregate millions of these atoms together, they will make these nanoparticles that have these dimensions on the order of a few nanometers. And that's where the colors come in.
Yeah, so you said 10 to the minus 9 meters or so, right? On
Yeah.
And so we have to actually manufacture them. They're not naturally occurring.
Oh,
the nanoparticles?
well, yeah. That I mean, of course, remember I said they were discovered, in ancient times. I suspect it was discovered entirely by accident, but it turns out using the methods that I just talked about, somebody must have figured out how to take silver, dissolve it in water, and then they added some sort of reducing agent. And again, there's just citric acid is commonly available, and and then just suddenly you discover, oh, this in the case of silver, you suddenly get this brilliant yellow color. And then in the case of gold, you get this brilliant red color. Okay. And of course, they wondered what that was. Why did there was this color change from something that was more or less colorless to something which had these nice colors. And so it turns out that that was a mystery, but it didn't keep people from making stained glass windows for centuries. Okay. And but it turns out finally, Michael Faraday, the famous Michael Faraday, who did many things in his career, as you know, well, it turns out in 1 year in the 1850s, he knew about the stained glass windows and other things that we now call colloidal materials, but they didn't use that term back in his days because that word hadn't been invented. But in any event, he decided, hey, I'd like to understand, what's going on with these colloidal silver, colloidal gold materials. And so he spent a year trying to figure this out. Okay, and among other things, he took the colloidal gold, so this brilliant, nice red color. Okay, and he said, well, okay, let's just evaporate all the water. What's left? So you evaporate the water, and what do you got of it? Gold. And of course, gold is gold color. Okay, and it's not red. Okay, so he was puzzled by that. And then another experiment that he did involved kind of doing the reverse. He said, okay, let me take a piece of gold and let me chop it up into little tiny the smallest things that you can still see. Okay. And what does it look like? Well, it still looks like little chunks of gold. Okay. It doesn't look red. Okay. So he was really puzzled about all that stuff and tried a bunch of other ideas with that. But eventually, after 1 year, he decided, I can't figure this out. I'm just going to give up. And if you look at his career as a whole, you discover that that's the sort of thing that he would do every so often. It's just say, can't figure it out. Time to move on. Okay, but it turns out that in the end, what he did was to let in other projects that he did, is he discovered many of the basic laws of electricity and magnetism that ultimately were written down by him, but eventually a guy named James Clerk Maxwell in the late 1800s, he discovered that you could write down equations that describe the fundamental electrodynamics of light. Okay, and it's based on Faraday's ideas, but it was a much more complete theory. And then that allowed somebody else to figure out, well, how does light interact with a nanoparticle of gold or silver, and what do you get out of that? So it turns out actually several people contributed to figuring all that out. But the person that usually gets the credit for it is a guy named Me. Okay, Gustav Me. And Me, in the early 1900s, developed a theory that's now called Me theory that describes the scattering of light and absorption of light by silver, gold, and many other particles. And it turns out you get results out of that directly that tell you, yes, silver is particles, colloidal silver particles have these brilliant yellow colors, and the gold has the brilliant red color, and many other versions of that.
So when you take a nanoparticle, George, I know nothing about this. So you said 10 to the minus 9 in sort of size of it.
Yeah.
How many atoms are on it?
Yeah. So yeah, in the end, it turns out that there's a trend. You can say, okay, I'm going to start with a few, say, silver atoms or a few gold atoms, and if I have two, is that a nanoparticle? No. Okay, and it looks like more like a molecule, and its properties are quite different than what I just described for nanoparticles. Turns out that usually it takes on the order of 100 or so atoms before you start getting properties that start looking like silver or gold, nanoparticles, as I just talked about them. And actually, so 100 atoms, roughly speaking, is about a 1 nanometer size nanoparticle. Okay, and then you need to get up to larger numbers before they become stable enough so that you can start doing experiments. So people normally don't do experiments with nanoparticles that are smaller than about 5 nanometers. And then the properties do change as you go to bigger ones. Actually, the most brilliant reds of gold are associated with particles that are 5 to 10 nanometers. By the time you get to 100, it turns out the optical properties changed a little bit. You get more of a purplish solution. It's not really as nice as the ones that are 10 nanometers. Okay, so that's an interesting result in its own right, which it turns out that again comes out of Me theory in terms of understanding why that happens. But yeah, so in the end, I always think of it in terms of numbers of atoms. It starts at around 100 atoms, and then it can go up to the millions or the billions or even the trillions. Okay, but the properties keep evolving as you vary the size of it.
So about 100 atoms. So can we think of a nanoparticle as sort of a fundamental structure? What I mean is that so we know atoms, we know molecules, we know large molecules with variety of atoms in there.
Right.
Is nanoparticles sort of a fundamental structure? Is there something, what I'm trying to think about is there some sort of physics underneath that says when 100 atoms get together, you get a nanoparticle?
Oh, well, yes. There's first of all, there's the issue of the structure. Okay, and it turns out that so silver and gold, when you make them into crystalline lattices, so macroscopic crystals, okay, they like to make these cubic lattices where the atoms are arranged on the vertices of cubes with certain structure. The one that applies to both silver and gold is called an FCC lattice. So what happens then is that when you make these small particles, like on the order of 100, actually the structures can be crystalline, like in the sense of forming these crystal-like lattices. Usually they're modified, they're distorted, they're too small to be a nice real crystal. Okay, so you get other things, but some of them have well-defined structures that are you can. They're beautiful structures, actually. They can be dodecahedral structures and things like that. The good news, though, is that these plasmon properties, the optical properties, they aren't super sensitive to exactly which structure you have. Okay, the results that most people think about are particles that are mostly spherical. Okay, and so think of it as being kind of a crystalline cubic lattice, but it turns out all sort of rounded off into a sphere. Okay, so that's the sort of the most common thing that you can make. Actually, you can make these in your kitchen, well, with the right materials and everything. And so so that's the standard thing. There's other versions of the story. Something that that has become a big deal over the last 40 years that I've worked on this problem are particles that are not spheres. Okay, and it turns out that you can make particles with lots of other shapes besides spheres. Okay, it's complex chemistry that allows you to do that, or you can make them sometimes with other methods like vapor depositing metal into cavities that have some shape. And so people have done that. And what it turns out, what is been known and further evolved as research has occurred, is that if you make a shape that's not a sphere, then you change the colors of the particles. Okay, so in the case and it's still just this plasma excitation, but it's sensitive to the shape of the particles. So something that's kind of cool is that if you make silver particles, but you make them as triangles of silver, right? So little triangular plates of silver, then you can change the colors of the triangles over quite a range in the spectrum. You can make these triangular shaped particles not that are just yellow as spheres are, but instead they can be colors, basically the entire spectrum of visible colors, basically going red to blue, okay, by just changing the dimensions of the triangle, making them the edge length and also the thickness of the triangle. So that's been done. The people make those, and so a nice thing about these plasmatic particles is that you can make them have almost any color you want if they're silver, and gold a little more limited, but still pretty good. And just by being able to control the shape of the particles that you make. So that's another fascinating aspect associated with these.
You talk about dielectric properties.
Yeah.
So what do you mean by that, dielectric properties?
Yeah, so that's another property that is surprising. Okay, so yeah, so the particles I've been talking about so far refer to particles that are in, say, water or dissolved. They're suspended in water, and so as I say, gold has sort of red colored particles, things like that. But it turns out that if you were to change to some other solvent, then that can change their color. That's an example of a dielectric property because water has an index of refraction, a certain value of it, and if you go to a different solvent, then you get a different index of refraction. And it's known that if I have particles suspended in liquids that have different indices of refraction, I can change their colors a little bit. So that's interesting. But then another thing that is in some respects more important is that if I have these particles suspended in water, then I get this color. But that's if they're in low concentration in water. If I start putting them closer together, I increase the concentration of these particles in water, or there's many other situations where that shows up. Then it turns out that also can change their colors. Okay, and actually, the best example of this was used in the standard test for COVID. Okay, that everybody has taken. Okay, this antigen test. So in that case, what you do is you have gold nanoparticles, and people developed the chemistry so that you could attach molecules to those gold particles. That was a big advance that took place mostly starting since the 1990s. And so you can take any organic molecule within a range and attach it to gold particles. So in this particular COVID test, you attach antigens, which are they're organic molecules, and you attach them to the gold particles chemically. There's a certain protocol that's required to make that happen. And then what happens is the particles in the COVID test, the particles initially are suspended in I don't know, some sort of matrix, whatever. They're in low density. So what happens is, though, although they are colored, they're not very strongly recolored. They're kind of spread around. But what happens then is if you then take a COVID virus, okay, and you expose that to these particles that have antibodies attached to the particles, then the antibodies will bind to the COVID spike protein, the antigen. Okay, and so what that does is that suddenly takes all these gold particles that were sitting around the solution, and it binds them to the little virus particles. Okay, and it turns out that brings all these gold particles together, and when you bring them together, that influences their color. It shifts them to actually a more brilliant red color. Okay, and so when you've taken the COVID test and you're looking for this red bar, okay, that's the gold particles. That's the plasmons in the gold particle that are resulting from the fact that they bound to the viruses. And so, yeah, there you go.
Yeah, that's awesome. So because it's nanoparticles and gold is expensive,
Yeah.
because it's nanoparticles, there isn't a lot of gold there, but you can still get a detection. You can still get a color, right?
Yeah, right. That's right. So that's an amazing thing associated with nanoparticles is that the price of the gold that's in those tests is just a cent or so, a few cents. Okay, and yeah, and yet there's enough of the particles there so that they interact with each other. Their plasmons all get coupled and everything. And so in the end, you can actually see the red color associated with that little tiny little bit of gold. Right.
Yeah. So you talked about the windows, the colors that we see in churches and other places.
Right.
We talked about COVID tests, where actually the technology is applied to get a red band. If anybody has tested positive, they would have seen it.
You know.
I have last month.
Yeah.
So there's some real practical applications, right, in many areas. And I was thinking in terms of computation, and so increasingly increasing the speed of computation is a big deal. There's sort of quantum computing ideas floating around. Do you see some applications there as well?
Yeah. So, but it's still evolving. Okay, this is now we're back to talking more about basic research. So I mentioned earlier me theory. Okay, me theory, which was originally developed 1908, was a way to describe the optical properties of particles in terms of light, thought of as being an electromagnetic wave that interacts with those particles. Okay, and the nice thing about me theory is that it's it's not a trivial theory, but you can apply it and you can use it to describe particles that are like 100 nanometers in size. Okay, so turns out that a lot of research is based on using that level of theory to understand what you're doing. Okay, so but what happened is that as the technology of nanoparticles got developed, people started getting interested in other properties. Okay, that besides just simply the me theory and looking at light scattering or light absorption by these particles. Okay, and so it turns out that gradually me and many other people have started to develop more quantitative theories because me theory is just electromagnetic waves interacting with the material gold. Okay, and so that's fine, but what you can't get out of me theory has to do with letting these metal particles, which are full of electrons, letting the electrons in those particles actually do something. Okay, participate in chemical reactions or other properties, and so this has gotten to be kind of a topic of great interest just in the last 10 years or so. Because people discovered that you could use gold particles and other metal particles as photocatalysts. Okay, so what that means is that you're taking a gold particle and you're exposing it to molecules that you'd like to initiate a reaction with. Then you shine light on the gold particles, you excite these plasmons that I mentioned before. And it turns out that when you do that, you end up getting electrons that come out of the particles and interact with the molecules that you put near to the particles, and that leads to chemical reactions. So the first experiments done in that were done about 10 years ago. And since then, that field just gets deeper and richer and so forth. And there's examples where people have looked at things like the getting water to oxidize, getting CO2, okay, to react and get reduced. Okay, and so reactions that we really would like to be able to perform at a vast scale very cheaply. Okay, it turns out that at least in some cases you can use nanoparticles to make those reactions occur. And so there's a great deal of interest trying to see, well, how far can you push that concept? So in the end, when we think about this, that means that we need to go beyond just simply with the me theory, the waves interacting with the material. And we actually need to be able to describe the particles in terms of what the electrons are doing in those particles. And so that's that's where you need quantum mechanics, okay? And you have to start digging into the details of just what actually are the electrons doing in those particles. And so that's where, I mean, there are methods that have been developed for doing that sort of thing. But in the end, because you have a lot of electrons, every silver and gold atom has a lot of electrons. And so that means then that the complexity of this problem is much higher than it is when you're dealing with the continuum like me theory. And so in the end, this has been an evolution for many of us. Back when I first started thinking about this stuff in the late 1970s, we said, oh, well, we need to do calculations then on these metal clusters, like with a lot of atoms in them. And so, so we did calculations on something on the order of about 10 atoms, and then if that was the biggest we could ever do, and so it's like, okay, well, can't do any very well with that. So that then evolved over the years. There was a lot of advances in electronic structure methods and related things. And so then, say 20 years ago, we did calculations on clusters that had like 100 to 200 atoms in them. And so that was pretty exciting to get to that point. Okay, but then it's like, okay, well, yeah, but remember I said 100 atoms is like the smallest you can possibly think of as far as of one of these types of particles is concerned. And we really need to go to bigger ones. So nowadays we're doing calculations with on the order of 1,000 atoms. Okay, so as the more you put in, the more realistic the results get. The closer you get to actually describing quantitatively what's going on in experiments. And so yes, that's an exciting evolution.
Yeah, I'm just thinking, George, how about
And with
3D?
quantum computers, we hope we can do a lot more. Okay, the scaling is just so much better with quantum computers, and so it's a goal to get to do that. Right.
Right. Yeah, it seems like a nice match there. How about 3D printing? Do you see some
Oh, okay. Well,
applications?
of course, the question you're asking me about is something that I was actually involved in that led to a paper that got published last spring. Okay, so it turned out that uh, I was working with a research group at Stanford University. The professor's name is Wendy Gu, and she was very interested in these clusters of silver and gold particles. Okay, similar to what I said before, where you have, in this case, these are somewhat smaller clusters. They were on the order of like maybe 25 atoms or so of gold, but well defined. You can make them, and you can make a lot of them. It was just synthetic chemistry to do this. And so we stayed with Wendy. We did a lot of work on the optical properties. We studied structures. She looked at pressure effects that were quite interesting. But it turns out one of her postdocs decided, oh, let's see what happens. So they do 3D printing in her group. Okay, and 3D printing is where you're trying to make polymers really fast. Okay, when you shine light onto the polymer monomers, plus usually there's some activator species in there that get the polymerization going. And in the end, I probably never would have thought of this myself. But what the student figured out was that if you take these 25 atom clusters of gold and you throw them in instead of the usual activator species that are used for 3D printing, that it actually works better than in the standard 3D printing. Okay, and
Yeah.
the mechanism of that is still not entirely clear. Okay, we've tried to do some modeling to figure out why it is that these 25 atom gold particles are so good. Okay, but in any event, it works spectacularly well. And so, I could imagine, again, remember I told you, these little tiny particles, they don't cost very much. Okay.
Yeah.
And so at the end, we can look forward to the possibility that someday, when you want to do your 3D printing, it's just going to be a lot better, faster, and more materials. You're not just stuck with the standard polymers that people. So yeah, that led to a paper that was published in Science magazine last spring.
Yeah, I mean, as you go micro, more and more micro, you could have technologies that sort of parallel printing as well, I would imagine, right? So maybe 3D printing will change in the future,
Yes.
potentially.
Yeah. Well, I think in the end, there's a lot of interest in 3D printing as far as just what materials can you make. Okay, and the standard 3D printers are mostly based on well-known polymers that polymerize well and can be light activated. I mean, there's a lot of reasons that we chose what they chose, but you'd like to make things with much more versatile possibilities. Okay, you'd like to use 3D printing to make metallic structures, things like that. And so so I think in the end is I'm not saying that these silver and gold particles are going to solve all problems, but at least there's examples where they have proven to be useful.
Yeah. I want to go into another paper you have, George. It's sort of related, discovering polyelemental nanostructures with redistributed plasmonic modes through combinatorial synthesis.
Yeah.
So you say here, coupling plasmonic and functional materials provides a promising way to generate multifunctional structures. Our finding plasmonic nanomaterials and elucidating the rules of various geometric and dielectric configurations are tedious. So um, if I don't understand this at all, George, but I'm thinking here is some sort of simulation, some sort of mathematical optimization of things, right?
Yeah. Well, that's the theory side of things, yes, and we're very much involved in that. But the other thing to realize is that the the you is that when it comes to making these metal particles, you'd like to be able to do it with lots of different compositions of many different metals. Okay, so this is so part of the story refers to some experiments that were done by one of my colleagues, Chad Merkin, where he developed a method that allows you to make particles. So again, these are just the usual nanoparticles. But it turns out that there's ways in which you can combine together many different metals into making each nanoparticle, and you can vary the compositions smoothly and continuously over a huge range. And so he's made particles. I mean, again, the sort of standards discussions, of course, I talked about pure gold, pure silver. You can make mixtures of gold and silver. Those are, we call those bimetallic. But then it's like you'd like to study the whole periodic table as far as the kinds of metals that you can make and what are the properties of the particles that you generate after you've made them. And so Merkin's group has figured out a way to make those particles and in such a way that they have you can systematically vary their properties, and from those you can try to optimize and find what's the particle that does some particular thing better than any other particle. Okay, and so there's many different versions of it. One of them is the optical properties that we've been talking about so far, but also there's work that they've done that relates to making the best possible catalysts. Okay, and so they can mix together, like we're working with them now on a project that involves mixing 4 different metals. Okay, and what composition, how much of each of the 4 that gives rise to the best reaction or best catalyst for, say, water oxidation or converting nitrogen into ammonia and things like that. And so those are that's a very exciting area of research that's just playing out right now, and it's basically arose because of this experiment. But in addition, we were in a position where we could predict the properties of many of these particles, but somebody had to really make them in order to make this into an important, technology. So that's now happening.
Yeah, so I'm thinking, George, there could be some AI applications here. So I mean, Northwestern is a material science school. So if I can go into the lab and I say, here are the properties I
Right.
want for this
Yes.
this thing, you go figure it out.
Right. And
From
that's already being
yeah,
done a little bit. It's just at the very beginning. But yeah, they have done the sort of experiment that you would expect, which is to say, okay, I'm going to mix together, various amounts of four different metals and make these little, 10 nanometer particles, and then see what reaction they catalyze or what optical property they have or something, some other property. And then in the end, the problem is a lot of information. Okay, I mean they can make on the order of billions to trillions of these particles in each one of their experiments, and it's almost like very hard to even absorb the information content. But what they can do is they can take the results of these experiments, feed them to AI, and then go back and say, okay, AI, tell me what's the best composition that I want for this property. So yeah, that's just at the very beginning of things, but it is starting to happen.
Yeah, but the beauty of this is that if we can sort of exactly prescribe the properties that we are looking for in a construct, and then we let the machine sort of create it based on data, humans are going to probably take a long time to get there. So I'm thinking, George, I don't know, superconductivity. I mean, we are missing some basic elements in material sciences, right? So do you see applications there?
Well, okay, so yeah, so the AI has been useful and is useful as long as you have enough data to train the AI or chatbot or whatever it is. Yeah. So that's why in the experiments I just described, okay, you literally have millions or billions of data points, and you can use those to train then the AI, and then the AI is going to give you a meaningful result. And so that's a terrific thing. Yeah. So I think in the end, there, that part of it, that's a good example where that's going to work pretty well. Yeah, I mean, but obviously there's always questions about what is can you apply that technology or idea more generally, and sometimes you have to have some basic idea as to what it is that's going on. We a lot of times use simulations as a way of generating data for AI, and then because you need to have a lot of data. If the simulations are good enough, then they'll give you you can use that to generate data or instead of experiments. And then you can use the AI to figure out, well, okay, what's the sweet spot in terms of something that you want to have happen. And so that's a useful way to do it. It's a little hard to use AI to extrapolate outside of the range for
Yeah.
which you have data. That's a dangerous direction. So yeah, so be careful. That's always what I always say. Yeah, right.
Yeah, so I want to finish up with your another paper, theory of entangled two-photon emission absorption between molecules. You say here the paper presents a comprehensive study of the theory of entangled two-photon emission absorption between
Right.
a many-level cascade donor and many-level acceptor
Right.
using second-order perturbation theory. And with the donor-acceptor pair, it's in a homogeneous but dispersive medium. Obviously, I don't understand this much, George, but there are many words here. The first thing is entangled photons.
Right.
So
Yes.
what happens there?
Yeah. So entangled photons are photons that have, in this case, say two photons that have, in a sense, know about each other. Okay. So yeah, these are little bundles of light. They're quantum mechanical in nature, and it turns out that you can, under some certain types of experiments, you can create two photons that are correlated or connected with one another in some sense. Okay, there's quantum mechanics involved.
So this is the
And
same, sorry, George, this is
yeah,
the same entanglement we talk about in physics, right? It's
yeah,
entanglement.
for communication technology. Okay, so in the end, it's actually a you know an area of communication technology that people are really trying to figure out how to take advantage of. Okay, because that's right. One example of this, okay, is that if you have two entangled photons, that means that when you detect one of those photons, the other photon knows that. Okay.
Yeah.
And so you can do an experiment where you do exactly that. You create these photons, say at the same point, space, and time, and then you propagate them separately. You can actually, there's experiments where people have separated the two photons by enormous distances. Okay, going from the Earth to a satellite, things like that. And then do a measurement on one and see does the second one know that happened? Okay, and it's really quite remarkable that works. Okay, so that's how entangled photons are already being studied for applications in communications. Okay, I have to admit the work that we've been doing has been more along the lines of trying to see whether the interaction of entangled photons with molecules leads to the, say, excitations in the molecules that are different than when the photons are not entangled. Okay, so there's something called two-photon absorption, which is a standard technology that's used in a lot of applications where you try to get a molecule to absorb two photons at almost the same time and go to a doubly excited state. And so people know that for unentangled photons. But the question is, what happens if you use entangled photons for that same experiment? And so
And they're
that's,
impacting the substrate at the same time, the entangled
yeah,
photons?
almost the same time. Okay, so typically there'll be small little differences. Well, there could be large differences, but the experiments that have done are ones where the two photons arrive, almost the same time, within, say, 100 femtoseconds of one another. And you can do that both with entangled photons or unentangled light. And it turns out that you get different results. Okay, so that's something that we got involved in fairly recently. We haven't yet connected that. Well, we haven't connected it with plasmons yet, but there are experiments that other people have done where they've tried to connect that with plasmons, because you can excite plasmons with two photons. Okay, and then the question is, well, to what extent, when you do that, do you get the plasmons to be different if they're entangled versus when they're not entangled? Okay, and actually there have been experiments done which show that exciting the plasmons with entangled photons leads to the properties of the plasmons that you produce that are different depending on whether they were, or different if they're entangled. And so that's that's really an exciting prospect, because you'd like to be able to excite these plasmons and then lead to different consequences in terms of what you're going to use those plasmons for. So we're still a long way. This is not practical technology. We're still just trying to figure out what's the basic physics involved. Yeah.
Hmm. So where do you want to take this research? I know that you have been involved in this for a long time. So where do you want to take it? So if you look forward 5 years, 10 years, where do you think this type of research will take us? Where do you see sort of the highest value applications might be?
Right. Well, of course, in the end, it's always unpredictable. I think that's,
Yeah.
if somebody had asked me, 10 years ago, are we all going to be taking a COVID test in which gold nanoparticle plasmons are the detection scheme for that? And I would say something like, well, I know it can be done, okay, but why would you want to do it? And it's like, oh, okay, son of a gun, okay. That happened. Okay, and so yeah, predicting the future is always a really tough challenge. I mean, I think we're still, that ultimately the plasmons give you a way to to convert light into excitations, and it's just a matter of how to take advantage of those excitations in different ways. And so I've been emphasizing. I've talked about some applications that are already kind of out there, but there are certainly other types of applications that I think we are still in the future. I know there's been a lot of interest, for example, in being able to detect single molecules, okay, with plasmons, and that's happened. Okay, there's ways in which you can use these silver and gold particles for medical diagnostics. That's actually a pretty well-known technology at this point. That I think actually early in your in this discussion, you were mentioning that I got involved in some papers with one of my other colleagues, Terry Odom, in which we were making arrays of these plasmon particles and then using them to make lasers. Okay, and so this was kind of one of these things that came out of nowhere. Okay, but it was more or less just driven by curiosity. Okay, it was like, oh, suppose I make an array of these silver gold particles. What are the optical properties that happen when this occurs? Okay, and so that was an idea that first came up in some work I was involved in about 20 years ago. And we discovered that there were these interesting collective excitations of all the particles in the array. So you could cite plasmons in every particle in an array. And it turns out that led to to excitations that were stronger and sharper than, in terms of their frequency dependence, than we could get out of any plasmatic particles with another method. And so then it was like, oh, so if I can do that, then what can I do with that result? Okay, and so it's like we're sitting around one day and saying, well, maybe you can make lasers out of it, because we already knew if you take laser dyes or quantum dots or something where you can excite molecules, then if you can excite them strongly enough, you can get them to laze. Okay, and so fortunately, Terry Odom had a brilliant graduate student who decided he was going to figure out how to make this work. Okay, and it took quite a while, but eventually the technology was mastered, and so that's now been around for about 10 years, and it just new things keep happening all the time in this area. So yeah, even though we're still trying to decide what's the best commercial applications associated with this, the fact that you can use that technology in so many different ways has just been exciting to see. So we'll just see where that goes. Maybe in your grocery store someday.
This appears to be a natural progression, right? So 10,000 years ago, we picked up materials from the wild, made instruments with it for agriculture and so on. And in Industrial Revolution, we started mining, we made metals and made automobiles, aircrafts, whatever. This seems to be natural progression. So if we get to a point that we say we can create an object by naturally depositing micrometals or nanometals in this case, then that is potentially much more efficient. I'm thinking, right? Is that where we're going?
Oh, yeah. Well, especially for something like catalysis, where you can just keep using the same metal particle over and over again to cause reactions occur that you want to make happen. And and so that's the big evolution of in catalysis, where it used to be that you would actually have particles that are big enough to see, and now we're down to small clusters, nanoparticles. Sometimes even individual atoms can be catalytic. So that's you don't need the plasmon properties for that. But yeah, sure. And so in the end, I think that's been to the benefit of mankind, that now you don't need vast quantities of precious metals to cause reactions to occur. You can certainly reduce the amount of precious metals by a lot, Okay, and then in some cases you can replace the precious metals by other metals that will cause the same reactions to occur. And that's this thing where you need to be able to explore the periodic table and understand all the different things you can get out of different types of materials.
Excellent. George, this has been great. Thanks so much for spending time with me.
It's been fun to talk.